Hello everyone, welcome back to LNT College Multimedia Studio. Today's lecture is focused on thermodynamic parameters and electromotive force of electrochemical cell. Right? So in the previous lecture, we have studies about the reaction mechanism of electrochemical cell and electromotive force, that is EMF of a cell, with the help of most important fundamental equation that is well known, and it is the Nernst equation, right? So by using the Nernst equation, we will try to elaborate some points that is most important in electrochemistry, and that will help to understand in the fundamental application of the electrochemistry, right? So what you have studies in the previous lectures, that is electrochemical series, right? The most important point in the electrochemical series is it gives us idea about the standard reduction potential of a particular elements, right? So today's topic actually involves thermodynamic parameter and its relation with electromotive force, that is uh, cell potential, right? So this is called E cell. So what are the uh, mechanism and function by which we can correlate this particular cell potential with thermodynamic quantities? Thermodynamic quantities means there is change in Gibbs free energy, change in entropy of the cell, change in enthalpy of the cell. Here, cell in the sense it is electrochemical cell, right? So, electrochemical cell, as in the previous lectures, you have studies that this is composed of cathode, anode, and electrolyte, right? So, suppose we have a galvanic cell or Daniell cell, then the anode is negative terminal and cathode is positive terminal, right? And anode is responsible for oxidation and cathode is responsible for reduction. And both cathode and anode, so they are connected through a salt bridge, right? And the main function of salt bridge is to maintain the neutrality in a solution, or uh, it will connect these two electrodes for the electrical conduction, right? And these two electrodes are actually connected by um, a outer circuits. So through this circuit, we will measure a volt or EMF of a cell. So suppose we have that is actually this is your first container, right? And this is your, suppose in the, so this is your first container, right? And this is your second container, right? As in the previous lectures you have seen. And this is one electrode and this is another electrode, right? Suppose we have a very good example, that is zinc copper galvanic cell, right? Galvanic cell. So this is your cell diagram. So this is your first electrode, this is your second electrode, and right. So and this is connected by salt bridge, right? So this salt bridge contains KCl, KNO3, that is strong electrolyte, right? So now this is, if this is anode, then this is connected like that, and this is connected with voltmeter, and this is voltmeter, right? So this is getting negatively charged and this is getting positively charged, right? So and this is the first container is, if there is zinc rod, then it has zinc sulfate aqueous solution. Okay, and if this is copper rod, so this copper rod is inserted in copper sulfate aqueous solution. Okay, so this is the combination of these two electrode to construct electrochemical cell, that is galvanic cell, right? So here zinc copper galvanic cell is constructed and they are combined with a voltmeter. So this is voltmeter that will measure EMF of this particular electrochemical cell, right? So this is electrochemical cell. So as you know that once the two electrodes are dipped in a particular of salt solutions, so if there is a potential difference between these two electrodes, and then it starts electrochemical reactions. So as you know that anode is responsible for oxidation and cathode is responsible for reduction. So zinc getting oxidized, so this is zinc solid, it is getting oxidized Zn2 plus aqueous plus 2 electron, right, at the anode. It means zinc is dissolved and go into the electrolyte solutions, right? So this cathode is positively charged and this is responsible for reduction reaction. So copper 2 plus, right, receives 2 electron and converted back to Cu solid. So these are the two reactions, so that are fundamentals in a electrochemical cell. That is actually once it is combined, then it creates overall cell reactions. So overall cell reaction is once zinc solid that react with copper sulfate aqueous solution. So the reaction proceeds, it is zinc sulfate aqueous and copper is precipitated out, right? So this is overall reaction in a particular zinc copper galvanic cell. So here what you have observed, so zinc solid, that is zinc rod, if it is dipped into copper sulfate solution, then the reaction starts and it ultimately forms zinc sulfate aqueous and copper solid, which is precipitated out on the cathode. So this cathode actually deposits copper, right? So this is copper. It means Cu2 plus from solution, it is ultimately reduced on the surface of cathode by receiving electrons. So this is external circuit, and from anode to cathode electrons are traveling, and at the cathode these electrons are responsible to pick up copper 2 plus and it is ultimately getting reduced. So this is copper solid. Okay, now this zinc solid, it is dissolved by oxidizing. So Zn2 plus, it is ultimately going into the solution, right? So if this reaction, or you can simply say if this half cell reaction occurs at anode and if this reaction occurs at cathode, so then these two half cell reactions, once it is combined and getting overall cell reaction like that, then there will be cell potential, and that cell potential can be measured by this voltmeter. So here this is V for voltmeter. So that is used to measure or for reading of electromotive force of this particular electrochemical cell, right? So what happens, this EMF, right, electromotive force or E cell of the galvanic cell, which is actually sometimes suffers with heat. So because of the charge transport in the solutions and ion exchange reactions in the solution, sometimes there is a heating effect, and that heating effect actually affects the cell potential or EMF value of a particular this galvanic cell, right? It means if there is a decrease of temperature or increase of temperature, so that electrochemical cell actually gets affected. So because of the resistance, either it will be high or low depending on the temperature of the particular setup. Okay, so this is what actually we have studies about the electrochemical cell. So for this system, you know that once this reaction occurs spontaneously, then E cell, right? So E cell is plus 1.10 volt. So here cell potential, that is 1.10 volt, right? So it is a positive quantity. So change in Gibbs free energy is negative. It means this electrochemical cell, once it is set up and it is thermodynamically feasible, means redox reactions occur spontaneously in the forward direction to form zinc sulfate aqueous plus copper solid, and its resultant cell potential is 1.10 volt, right? And that is why they gives a change in Gibbs free energy, that is negative. So if this reaction occurs at 25 degrees centigrade, then it will be E naught cell. Standard cell potential, that is 1.10 volt, and hence it is standard Gibbs free energy change, that is negative. Okay, so this is standard cell potential can be affected because of the variation of the temperature or thermal energy in these containers, right? So what happens here, we first understand equilibrium constant, right? So by using the Nernst equation, we will try to understand what is the role of equilibrium constant in a particular kind of electrochemical cell. Okay, so equilibrium constant, that is abbreviated as K, right? So in thermodynamics, what we have studies, delta G is equal to minus RT ln K, right? In thermodynamics, what you have studies about equilibrium constant, it is related to change in Gibbs free energy. So here change in Gibbs free energy at any temperature T is equal to minus RT ln K, right? Where K is the equilibrium constant. So it is under non-standard state, and if this reaction is thermodynamically significant, then under standard state delta G naught minus RT ln K. Okay, so this is the change in Gibbs free energy and its relation with equilibrium constant, right? So this is the general terms which are used in the thermodynamics, but in electrochemical cell, we are trying to correlate this equilibrium constant with cell potential, that is EMF. Okay, so suppose we have delta G is equal to minus RT ln K, right? So as you know that Once the electrochemical cell is constructed, then there is a overall redox reactions which occurs spontaneously in the electrochemical cell, and we get a overall cell potential, and this cell potential actually varies according to the variation of the Nernst equation and its parameter, right? So as you know that Nernst equation, E cell is equal to E naught cell minus RT upon NF ln Q, right? So this is the Nernst equation. So this Nernst equation, it is for electrochemical cell. It means once there is a anode and cathode which are dipped in respective salt solutions, and the potential which is generated in the electrochemical cell, that is E cell, right? And this is standard E cell minus RT upon NF ln Q. So Q is the reaction quotient, right? So Q is called reaction QUOTIENT, reaction quotient. Okay. So, and you know that it is actually ratio of the concentration of the product upon ratio of the concentration of the reactants. So, as you know in the earlier lectures. So, here what happens if Q is replaced by K, right? So, it means if reaction quotient approaches towards equilibrium state, then equilibrium constant K. At this state, E cell will be 0. Once the electrochemical cell reaches towards equilibrium state, it means forward reactions and backward reactions, they are actually be in equilibrium, or the rate of forward reaction will be just equal to the rate of backward reactions. So they exactly cancel to each other, and the resultant cell potential will be 0. So once this happens, then E naught cell will be RT upon NF, right? ln Q. Sorry, this is not Q, this is K. Right? So it means once you substitute this, ln K is equal to NF E naught cell upon RT, right? So if we have a electrochemical cell reactions, and we just balanced all the half cell reactions and overall cell reactions, then we will get the value of N, which is the number of electron transfers in the overall cell reactions, and F is the Faraday constant, which have a value 96,500 coulomb per mole. R is the gas constant, and T is the temperature. So if these four parameters, if we keep the value in this particular expression, and E naught cell and standard cell potential, whatever cell potential that will be measured by the voltmeter. So if you put these values, we can get ln K, right? And ultimately by taking the antilog, we can find out the equilibrium constant, right? So larger the value of equilibrium constant, so that favors the formation of the product. It means the reaction undergo spontaneously into the forward direction and thermodynamically favorable or feasible, right? So if the value of K, that is equilibrium constant, is low, then the reaction favors backward directions, and the chances of formation of the reactants is very high. So that decides actually the cell reactions and its directions, right? So this is the importance of the actually equilibrium constant in a electrochemical cell. And here that is you know that delta Z is equal to NF E cell, right, minus RT ln K, right? And so here again ln K is equal to NF E cell. So if this is at standard state, then it is standard state, right? So NF E cell upon RT, right? So if you here put for zinc copper galvanic cell, then N is equal to 2 and F is equal to 96,500, R is equal to 8.314, T is to 298 Kelvin. Then it will be, but just we can understand by putting these values. So this is actually E base. So K is equal to exponential minus NF RT E cell, right? So the variation of equilibrium constant with E naught cell look like that. It means equilibrium constant, if it is plotted on y-axis and with respect to E naught cell, right? So this is exponentially increases. This is exponentially increases, right? So equilibrium constant actually with time it is exponentially increases in a electrochemical cell that conforms the direction of the forward reactions. It means there is a high chance of formation of the product, right? So this is what is the equilibrium constant that can be understood through the thermodynamics and electrochemistry. Okay. Now I coming across to the point number 2, right? So point number 2, what is point number 2? So this point number 2, it is telling it is actually temperature coefficient of EMF, right? So temperature coefficient, what is temperature coefficient? Let us define temperature coefficient. So this is we have shown that what is temperature coefficient. So temperature coefficient, first we will understand what is temperature coefficient, as you know that it is related to temperature, right? So once a electrochemical cell or Daniell cell formed, so what happens here? So if there is a heating effect or change of temperature in a electrochemical cell, then the cell potential will be affected and overall electrochemical cell will be affected, right? So if so it can be understood either for single electrode or half cell reaction, or it is for whole electrochemical cell. So we have actually for a single electrode, right? So suppose once a metal rod is dipped into its salt solution and then it is connected through the potentiometer, then potentiometer can be can give about the information of the cell potential, and this cell potential may be fluctuated depending on the temperature or heating effect of the electrolyte solution. Okay. So this temperature coefficient actually defined as constant pressure. So TC, temperature coefficient at constant pressure, right? So it is defined as change in EMF or cell potential. This is your cell potential with respect to change in temperature at constant pressure is called temperature coefficient. So this is temperature coefficient. So this is for actually electrode reactions. So here we just remove the cell. So this is for particular only single reactions. So this is d upon dt at constant pressure. But for a electrochemical cell, so here temperature coefficient at constant pressure is d is cell upon dt at constant pressure, right? So this is what we define temperature coefficient. change in E cell or change in electromotive force with respect to change in temperature, we call it as temperature coefficient at constant pressure, right? So this is the variation. This is the variation, right? So if you increase the temperature, accordingly cell potential will be changed, and if you decrease the temperature, cell potential will be changed. Because in the Nernst equation, what you have observed, so E cell is equal to E naught cell minus RT upon NF ln Q, right? So this is your Nernst equation for electrochemical cell. Here what have observed? So this E cell is directly proportional or directly related to the temperature. In the they have two parts. So this is standard reduction potential of the cell, and this is these are the parameters, right? So what happens here, if you increase the temperature, overall these values will be high and E cell will be low, right? So E cell will be low. If you increase the temperature of the electrochemical cell, then the resultant cell potential of the electrochemical cell will be low, or it is decreases as the increase of temperature, right? And in a other words, you can say, if you decrease the temperature of the electrochemical cell, then E cell will increase. So this can increase or decrease depends on the temperature, and once the temperature is affected, the resistance of the solution also affected. So because you know that charge transport or ion transport actually depends on the resistance of the solution. So if higher the temperature, so lower will be resistance of the solution, or lower the temperature, then higher will be resistance of the solution. So as per the behavior of the electrolyte or behavior of the solutions, so the ion transport, charge transport, or redox reactions or rate of the redox reactions, that may get affected. Okay, so in this way we can understand. So this is the variation of the E cell with respect to change in temperature, which is called temperature coefficient. Okay, now coming across to third point, right? Temperature coefficient, this is third point, gives free energy delta Z naught cell at standard state. So delta Z naught is the change in Gibbs free energy at 25 degrees centigrade. So as you know that once the electrochemical cell is set up, it means once the anode and cathode, they are properly connected to each other through the salt bridge, and externally they are connected through the voltmeter, then there will be a redox reactions if there is a change in the Gibbs free energy. So because we are getting the conversion of chemical energy into the electrical energy, right? So once the chemical energy is converted into electrical energy, so there is some sort of work, so that is actually performed by the electrochemical cell, because we are getting work from the electrochemical cell. So electrochemical cell is a system, and we are getting actually energy. So it is you can say the work done by the system on surroundings. So it is always negative, and this work is actually equivalent to the change in Gibbs free energy, right? So delta G will be minus W max in a electrochemical cell, right? So this W max, actually what is W max? This is electrical work, that is maximum electrical work is W max. So it is actually product of the number of electron transferred in a half cell reactions or a overall cell reactions, right? So this is uh, uh, W max, and W max proportional to N, right? Number of electron transferred in a redox reactions or electrochemical reactions. And this W max also proportional to that is E cell, right? So these two parameters, they are directly correlates the maximum work that is obtained in a particular electrochemical cell. So overall, that is electrical work W max is charge, you can say W max, and we just open the proportionality constant and we will get F is the Faraday constant and F E cell. So we just put this and F E cell here. So this is delta G minus N F E cell. So change in Gibbs free energy is always a negative quantity, that is N number of electron, F is the Faraday constant, and E cell is the cell potential of a electrochemical cell. So if this E cell, right, E cell is positive, then delta G is negative. And in thermodynamics, what you have studied is, if change in Gibbs free energy is negative, then the reaction undergo spontaneously, right, in the forward direction. So, and if there is a delta G change in Gibbs free energy is positive, then it will undergo in a reverse direction, or it is a non-spontaneous reactions. So change in Gibbs free energy gives us idea about the direction of the redox reactions or electrochemical reactions in a particular galvanic cell. Okay, so this is what delta G stands for. Now this is in thermodynamics, delta G naught equal to minus RT upon ln K, and this is the actually delta Z. Once we put the value delta Z is equal to minus NF cell, then this is actually happens in this way, and the graph look like that. Now this is your electrochemical cell, what I have justified in the previous. Now this is delta Z is equal to minus NFE. So if we have a particular electrode reactions, either cathodic electrode reactions or anodic electrode reactions, so we will get this delta G is equal to minus NFE. So E is the electrode potential, either it is cathodic anode potential or anodic potential. So depends on that. If we have both cathode and anode, and once they are coupled to each other to construct a electrochemical cell, then we have a cell potential, and the change in Gibbs free energy that is equal to maximum work that is obtained by the electrochemical cell. So this is will be minus NFE0 cell, right? So this is for spontaneous reactions, and this is spontaneous. This is also for spontaneous reaction, but it is occur at standard state. It means if you have a 25 degree centigrade and 1 molar concentration electrolyte solutions and 1 atmospheric pressure, then we can define this change in Gibbs free energy at standard state, which will be minus NF E naught cell. Okay, so these are the ideas which can gives us about the change in Gibbs free energy. And from this equation, from this equation, just you can graphically understand. So suppose we have a x-axis and this is your y-axis. So this is actually is equation. It look like the straight line equation, that is y is equal to mx. It is actually negative direction, so this is minus nmx. So minus nf, that is slope, and E cell is the on E axis. right? So this is actually decreases delta G. So once cell potential increases from lower to higher value, then change in Gibbs free energy linearly decreases, right? So if we uh, increase the cell potential with a time, then change in Gibbs free energy decreases linearly, as you can see this graph, and which is plotted for delta Z equal to minus NFE cell. So similarly, you can plot at standard state. So this graph can insight you about the variation of the change in Gibbs free energy of a galvanic cell. Okay. Now another parameter, that is entropy change. So as you know that once the electrochemical reaction occurs in a cell, then there may be possibility that uh, randomness of the reactant molecules to form the products. So if there is a increase of randomness in the electrolyte, so because of the reactions and as a result the formation of the product, so entropy may be increased, so depending on the cell potential. So it can be uh, rationalized with the help of EMF of the cell. So what here we have actually taken from the variation, that is in thermodynamics you can actually define delta S is equal to minus D delta G upon delta T, right? So in the thermodynamics, change in Gibbs free energy delta G with respect to change in temperature, it is called change in entropy. Okay. So here we have a electrochemical cell or galvanic cell, right? So in galvanic cell there is a half cell reactions, or you can say there is a cathodic reactions and anodic reactions, and overall they are coupled to each other to give his cell reactions. So once a cell reaction occurs in the forward direction, so there may be chance of either increase or decrease of the entropy. Okay. So this is the variation of the change in entropy of the system with respect to change in Gibbs free energy with delta T. Now you know that delta G and FE, so if there is a cell reaction, then E cell, right? So delta S minus D minus NF E cell upon dt, right? So minus minus here positive, and then NF is constant, it can be taken out, and delta, so E cell upon dt, right? So this dE cell upon dt is called temperature coefficient, and delta S NF Tc at constant pressure. So here from this relation you can understand easily change in entropy of the galvanic cell, that is cell here, right, will be equal to NF, number of electron transferred in a electrochemical reactions, and F is the Faraday constant, and it is temperature coefficient. If you increase the temperature coefficient, then the entropy change of the cell will be increases, and if it is decreased, then cell entropy of the cell will be decreased. So overall change in entropy of the uh, cell reactions will be guided by the variation of the temperature coefficient in a electrochemical cell. So it is directly related, right? So change in entropy of the cell is directly related to the number of electrons transferred in a cell reactions and temperature coefficient. So if temperature coefficient is high, then change in entropy of the cell will be very, very high. So this is what is the variation of the change in entropy of the electrochemical cell with respect to the temperature coefficient. Okay. So this is what we have shown here to understand the entropy of the cell. Okay. Now we coming across enthalpy change. So change in enthalpy of a reaction, electrochemical reaction, that is, actually we get just change in Gibbs free energy, change in entropy. So similar to the change in Gibbs free energies and change in entropy, we just define here delta H, and if it is at standard state, then it is delta H naught, right? Now, as you know, in the thermodynamics, the relation between change in Gibbs free energy with respect to temperature and entropy look like that. So this is delta G is equal to delta H minus T delta S, where delta G is the change in Gibbs free energy of the system. Here system is electrochemical cell, that is galvanic cell, right? So in galvanic cell, change in Gibbs free energy is always negative, and if there is a delta H, so where we have to find out delta H. So this delta H is equal to delta G plus T delta S. So both terms can be added here. So delta H is equal to delta G is equal to minus NFE, which is actually earlier we have defined delta G, and plus T, and delta S means NFTCP at constant pressure, right? So delta H overall NFT d upon dt at constant pressure minus NFE. Now by arranging this, delta H naught at standard state, so this is actually variation. So here NF is the common, you can take it out, NF, and the variation look like that, T dE naught cell upon dt, right, at constant pressure, minus E naught cell, right? So this is the variation delta H. So if there is if this delta H naught is negative, it means this favors the formation of the product, or you can simply say the reaction is exothermic. It means there is a chances of the increase of the temperature of the electrochemical cell, and if this delta H naught is positive, and then it gives us idea whether that this electrochemical cell may be operated at endothermically. It means there is a need of the temperature to happen the reactions. So exothermically or endothermically, that will be actually calculated through this particular variations. So this delta H naught directly related to the number of electron transferred in the electrochemical cell, and it is also depends on the dE cell upon dt, that is temperature coefficient. So the temperature coefficient decides the value of this delta H naught, so change in enthalpy at standard state. So these are the thermodynamic parameters which are supposed to understand or must be clear to understand the electrochemistry of the cell, right? Now we coming across last topics, that is standard hydrogen electrode. We'll try to finish it by 5 to 10 minutes. So that is standard hydrogen electrode. What is standard hydrogen electrode? So as its name, it is derived standard. Standard means just a electrode that is operated at standard state, that is 25 degrees centigrade and 1 atmospheric pressure and 1 molar concentration. So that is standard state. Hydrogen, so it is actually hydrogen, H2, that is hydrogen. Electrode means, so we have a wire that is actually platinum. So this is the composition of a standard hydrogen electrode, that is platinum, that is conductive electrode, and H2 is the hydrogen gas, and H plus is the 1 molar concentration of acid, that is HCl or H2SO4. Okay. Now here we have shown diagrammatically that how a standard hydrogen electrode look like that. So we have a inverse U shape glass, so which contains a platinum foil. So they are connected with wire, right? So and they are externally they are connected with multimeter or potentiometer, right? So this platinum plate is stripped, so they are dipped in the electrolyte. So here electrolyte is the HCl, that is H plus and Cl minus. So it contains H plus plus Cl minus in the solutions. Okay. Now this is the outlet where hydrogen gas at 1 atmospheric pressure, it either enters into the reaction medium, or it will go outside to the cell. So there is two possibility there. Either hydrogen gas can be created, or hydrogen gas may be supplied to the system. So this platinum electrode, actually it is kept in the electrochemical series below to the hydrogen. So they are less reactive, they are very inert, and that is why they are taken here as a electrical connection for this kind of electrode. So as you know in the previous lectures, that is electrochemical cell and electrochemical series. So hydrogen, that is 2H plus, right? Once this receives 2 electron, it is converted back to hydrogen, right? So this is the half cell standard reduction reactions, and this standard reduction reactions have a standard potential, that is E naught is equal to 0.00 volt, right? So it has zero standard reduction potential, right? So once this platinum electrode is coming into contact with the HCl electrolyte, so there may be either oxidation or reduction of the H plus. So this contains actually H plus and Cl minus, right? So this, if there is a reduction of the H plus, then the reaction happens like that. So once 2H plus and 2 electron, and this is converted back to H2, or it can be H2. So this is 2H plus, and then 2 electron is released. So it occurs if this electrode act as a anode, then there may be chance of oxidation of the hydrogen. So it is converted back to hydrogen ion into the solution by releasing the 2 electron. If this electrode works as a cathode, then there may be reduction, and it will favors the formation of hydrogen gas by the reduction of hydrogen ion with respect to the electron. So this can be act as a reference electrode, because it has a zero potential. So either it is oxidized or reduced. In both cases, so they have zero voltage. So by adopting this kind of particular electrode, we can couple another electrode to construct a electrochemical cell. So it is acting as a reference electrode, and it has a zero standard reduction potential. So just we want to write the Nernst equation for this electrode. Then what happens? Suppose we have a reaction like that, 2H plus plus 2 electron, it is getting H2, right? So as you know that delta, not delta, it is E cell, right? Or it is not cell, simple, it is a single reactions. So you can here E H 2H plus, that is H2. E naught 2H plus, that is H2 minus RT upon 2F. Here N is the 2 electron, that is N is equal to 2. And that is ln H2 upon H plus का whole square. Here hydrogen is the free gas. So here concentration or activity of the hydrogen gas is tending towards 1. So this will be E2H plus H2 E naught 2H plus H2 minus RT upon 2F ln 1 upon H plus का whole square, right? So here simple mathematics, E to H plus H2 E naught to H plus H2. Here if this denominator go into the numerator, then here will be minus 2 power, then it will come out to the, then this will be plus and 2 RT upon 2F ln H plus, right? So 2 it will be cancel out. Now E to H plus H2 E to H plus H2 plus RT upon F ln H plus. But in physical chemistry you have know that is actually in next page. E 2H plus H2 E naught 2H plus H2 plus RT upon F ln H plus. So if you put the value of R and temperature at standard state to 98 Kelvin and F is the Faraday constant, then it will be just E 2H plus H2 E naught 2H plus H2 plus here 0.0591 log of H plus. So here ln, that is converted into log. So log is 10 base and ln is E base. So just we want to convert this E base into 10 base, then we just multiply 2 point. Here this is multiplied by 2.303, and overall if you put the value of R 8.314 and T is the temperature to 98 Kelvin and F is the Faraday constant, then we will get 0.0591 log H plus. And you know that pH is equal to minus log of H plus, right? So here you can put E2H plus H2 E naught 2H plus H2 minus 0.0591 pH, right? So here you can say 0.0591 pH is equal to E naught 2H plus H2 minus E2H plus H2. So this is the value we can get from the electrochemical series, that is 0. So pH equal to minus 1 by 0.0591, that is E2H plus H2. So pH is equal to minus 1 by 0.0591 E 2H plus H2. This is the relation. So ultimately pH is equal to E2H plus H2 upon 0.0591. So this is the relation between the EMF of the galvanic cell and with respect to the pH. So pH is directly related to the E cell of the or E electrode of the standard hydrogen electrode, um, uh, that is reference electrode. So variation of this value will affect the pH of the solutions. So in this way, we can understand that through the coupling of this standard hydrogen electrode with respect to other electrode, we can generate a multiple number of galvanic cell and hence cell potential. So if you want to measure the cell potential of copper and with respect to the hydrogen electrode, then you will get EMF as that is, suppose we have a copper and we have a standard hydrogen electrode. So by coupling these two electrode, we can get EMF, that is 0.3 volt. Or if we couple this zinc with respect to a standard hydrogen electrode, right? So then we can get EMF, that is 0.76 volt. So any kind of elements and its half cell reactions that is connected with the standard hydrogen electrode, so we can get the EMF of a galvanic cell. So standard hydrogen electrode sometimes may act as a anode and may sometimes act as a cathode, and overall cell reaction will be E cell is equal to E cathode minus E anode, and that decides the generation of the cell potential for that particular electrodes or elements. So this is the chemistry and electrochemistry that facilitates the understanding of the cell potential or EMF in a galvanic cell. So through the knowledge of this standard hydrogen electrode, that is reference electrode, we can construct a multiple number of galvanic cell and there can be estimated a cell potential. Okay, so this is what is enough to your level, and you can study about these parameters that I have previously explained you nicely, and the simple mathematical relations and graphical representation, that I think that much is enough to understand the basics and fundamentals. So okay, thank you students for listening and watching this video, and again I will meet you with a next video. Okay, thank you. आप काट दीजिए.